Hi, myself I am Praveen. Today I am going to discuss a famous questions that usually appear in our exams. So let's start discussing about full adder. Realize a full adder circuit using only 1:4 DEMUX. So it is a demultiplexer and I am going to discuss how this demultiplexer functions. Okay, using only 1:4 DEMUX. First of all, in the full adder we do have to note that the sum and the carry bit minterms. So the sum bit minterms and carry bit minterms of a full adder is as follows: 1, 2, 4 and 7 are the sum bit minterms and the carry bit minterms are 3, 5, 6 and 7, which we see as according to this truth table. So I am not going to discuss here the full adder, but I am going to discuss here the DEMUX applications or the DEMUX, how we can utilize the DEMUX as a full adder circuit. Okay, so let's suppose here this is the select lines for the DEMUX and this is the input. For activating the DEMUX, I will supply the input with plus 5 volt plus 1 logic, and the output we have total 4. This is 1:4 DEMUX, so we have the 2 selections line. I will make this 2 selections line as a data lines, and then after let's see here first in the truth table, B and C I have made as the select lines, so I can choose this D1, D4, D1, D5, D2, D6 and D3, D7 as accordingly. So let's suppose here what I am saying, if I choose 0, 0, so 0, 0 where I can see here 0 and 0, again here 0 and 0, means it simultaneously choose both of this. It simultaneously choose both of this order. What is this? This is a D0 and this is a D4. Okay, so they have chosen this both. What decide? Either this will be functional or this will be functional. This decision goes to A. If A is 0, the D0 will be functional. If one is if the A is 1, the D4 will be functional. So the decision made by A whether the D0 is functional or D4 is functional is based on the value of A. How do we input the value of A? So let's discuss here first. I am going to design this output as a carry bit, not as a sum bit. Okay, so I see here the minterm as 3, 5, 6 and 7, whose output will be always 1, 1, 1, 1 logic. Okay, fine. See here in this truth table we will see 1, 2, this is 1, 2, 4 and 7 for sum bit, for carry bit 3, 5, 6 and 7. So we don't have here 0, this is D0, 0 and we ignore here 4. Why do we ignore? Because we didn't have a, I am going to design a carry bit here, sorry, I am going to design here a carry bit, so its output is 0, so I am going to neglect this. So normally open, I will put the first as normally open, then after 5 and 1, this D1 and D5. D1 and D5, how to choose D1 and D5? If I choose here 0, 1, this is, if I choose here 1 and this is 0, so see here where we have 0 and 1, this is 0 and this is 1, again 0 and this is 1. So we have this 2 choice, but this will signal here. Okay, this will connect here and it will read this D1 and D5. So D1 0 1 and 0 1 and this 0 1. Now the decision is based on how the A will function, how the A will give its input. If A will be 0, then the D1 will be functional. If A will be 1, then the D5 will be functional. Similarly, we see in these two cases 1 and 0, 1 and 0. So we put here 1 and 0. So it will connect here. It will read the data line of D6 and D2 and D6. So the decision is based on how we will give the input A and how we will give the input A. Okay, so I can give as 1 or 0. So the decision is based on how the A will be functional, whether 0 or 1. So I will connect this to the AND gate and another AND gate. Okay, as if I assume here 1, if I assume here 1, the D7, D6, D5 or D4 will be functional. But if I put here 0, then D0, D1, D2, D3 will be functional. Now see here, I have to read the data line. So let's suppose this connected here. So this is 1 and 0. And if I put here 0, D2 will be functional. So this will be have as D2 and it reads the data line of D2 as an output. But at an instant, if I put here 1, so D6 will be functional, and D6, as the D6 will be functional, it reads the data line of D6 and this how the output of the carry bit will be functional. Now see here, we have A as 0, 1, B also has 0 1 and C also has 0 1, whatever the input we can give. This all I will connect this with XOR gate, and this how we will realize a full adder circuit using only one 1:4 DEMUX. The main thing to note here is do remember this. For full adder, for half adder I am going to, so for half adder similarly you do the questions for half adder. See the difference bit for half full adder, difference bit for full subtractor, sorry, the difference bit for full subtractor is 1 2 4 and 7. Similarly the borrow bit for full subtractor is 1 2 3 and 7, and you can design accordingly. Okay, fine, thank you.